Okay, so let's get started. That said, I want to start my talk. I will not go too heavy on the number theory since that's not the goal here this weekend. But I want to start my talk with a notion from arithmetic geometry that motivates everything I'm going to talk about. And that's the principle of unlikely intersections. And let me start introducing you to this with an example which should be familiar to many of you, which is the following question. So, sorry, let me first ask another question. Can someone give me like a couple minutes flag? There's no clock in here. Yeah, thanks. Okay, great. So the question is as follows. Let's suppose I take a curve inside of a plane. So let's let C be an irreducible algebraic curve in C2. In other words, this is the collection of points which lie on the root locus of some polynomial, right? So, okay, sorry, xy. And we'll assume it's irreducible just for simplification of the statement here. And the question is, when is it possible for this curve to have infinitely many points where both coordinates are rational numbers? Okay? So when can C have infinitely many points with both coordinates rational numbers? Okay? Okay, well, there are some silly cases, right? Like if you take a horizontal or a vertical line over a rational number, or if you take the diagonal, something like that. In fact, it's pretty easy to say when lines will have infinitely many rational numbers, right? All we care about is their slope and a point that they contain. Okay? So it's possible for lines, though it doesn't happen all the time, of course. Say if my line is x plus y equals pi, I'm not going to do so well. Okay? But that's not the only setting. It's also possible for things which are not obviously lines, like, say, x squared plus y squared equals 1. Right? What is a rational point on this curve? Well, if I take common denominators here, what I get is integers which are of the form x squared plus y squared equals z squared, right? In other words, Pythagorean triples. And we know there are infinitely many of those. Okay? There are some other less obvious possibilities, but this question was fully answered by Faltings, though we knew for more than 100 years now that the answer should be, even though this question is entirely number theoretic in some sense, right, because we're talking about rational points, that the answer should be geometric or topological. Okay? And this is what Faltings' theorem says, is that C has infinitely many points which are rational only if the genus of C is, 0 or 1. Okay? And I'm being a little sloppy here because I have these plane curves. They're not, for example, compact, right? But you could imagine taking a projectivization and compactifying by adding points at infinity here. And then this is the genus I care about. Okay. So this genus, of course, is a totally topological thing, right? So we're just talking about number of handles, as I learned 11 years ago. We're just talking about number of handles of this curve when we view it as a Riemann surface. Okay? So here's my genus 0 case, and here's my genus 1 case, and here's my genus greater than 1 case. And if you look at this theorem, it doesn't make any sense, right? Like, why do you expect this topological constraint to say anything about rational points? Okay? And so I want to rephrase for you the statement of Falting's theorem in terms of unlikely intersections, and then it will all be crystal clear. Okay? So what's the idea? The idea is the following. So over the complex numbers, curves of genus 0 are essentially, at the end of the day, the Riemann sphere. Okay? And curves of genus 1 are elliptic curves. And what these two objects have in common is that they contain groups. Yeah? So group laws given by addition, or if I want to look at the multiplicative group inside here, group laws given by addition or multiplication inside of these curves. Maybe not defined on all of the points, but on all but finitely many of the points. Okay? So these are groups. Okay? So what does that do for me? Well, what's the point? The group law in both of these cases preserves the property of rationality.
Stupid question,
right?
since you encourage them.
Yeah.
Consensus if you want a group.
So minus finitely many points. Minus 1 point. Or if you prefer multiplication, minus 2 points. Yes, you're certainly right. Yeah, if I want to include infinity in the picture, then it's not such a nice group. But in what I'm about to say, you'll believe me that it's enough to have it be true on a dense set. Okay? Other questions since we're pausing for a second? Okay. So the point is that not only are these things groups, I should probably move over here. Not only are these things groups, but they have group operations which preserve the property of rationality. And so the restatement in terms of unlikely intersections is the following. So C has infinitely many points which are rational if from one finite or finitely many rational points infinitely many can be constructed. Okay? So this is the reinterpretation, which it's not topological. Okay, now because there aren't that many curves in the world, it's equivalent to a topological statement, right? But the statement is essentially that the only reason why C might have infinitely many rational points is if C comes equipped with this rule, in this case the group operation, which takes a single rational point and by adding it to itself gives you infinitely many. Unless maybe you started with a torsion point and then you don't get infinitely many. But this is an only if. Yeah? Okay. So this is a rephrasing of Falting's theorem. And what is the statement in the sense of unlikely intersections? So here's a very vague statement. So this philosophy is attributed generally to Pink and Zilber, which is the following. So if a geometric object, I like algebra a lot, so I'm going to work with varieties. Or if you don't like algebraic geometry, that's fine. You can just think of curves, like we did with Falting's theorem. So if a geometric object has, well, and again I'll put in parentheses, so lots is the nonspecific statement. If I'm talking about varieties, lots means Zariski dense. If I'm talking about curves, lots means infinitely many. Okay. A geometric object, sorry, let's say it this way. A geometric object has infinitely many special points, or Zariski dense special points, only if it is special. Okay, so this is a very broad statement and very vague, and that's on purpose because I want the word special to mean a lot of different things. Okay? Now, in the setting of Falting's, special means rational, right? Or equipped with a group operation that preserves rationality. Okay? But it can mean a lot of other things. So what does special mean? Here are some things that it can mean. So first of all, rational. It can also mean torsion. So if my geometric object is a group, like in these cases, right, I can ask about when that geometric object has lots and lots of torsion points. Okay? This falls under the setting of conjecture, now a theorem in algebraic geometry known as Manin-Mumford conjecture. Okay? It can mean a property of a moduli space of something, like complex multiplication, and so on. I'm not going to worry about any of these things, which is why I'm not defining them. It's just a commentary for if you've seen them before. Okay? So there's a lot of different interpretations, but what Pink and Zilber say is that there's this moral idea, this philosophical idea in mathematics, that if your variety or your curve or your manifold or whatever has lots and lots of special points, then there's got to be a good reason for it. Okay? All right. Okay, any questions before I completely change gears? No? Okay. Then let me tell you what special means to me. So special to me means dynamically special. So let me give, first of all, a little bit of an intro to polynomial complex dynamics. Okay. So the basic object of study here for me is going to be a polynomial. Okay, so let's let, say, f of c be a polynomial, which for the moment can just have complex coefficients. And I'm interested in studying this thing under repeated application, under iteration. Okay? Now, this turns out only to be an interesting problem if the degree of this polynomial is at least 2. Okay? And let's give these iterates a name. So usually, probably, you might be used to seeing a circle here for composition and iteration. But since I do dynamics, I don't like drawing circles all the time. So I'm going to let this be shorthand for the n times composition of f with itself. Okay? All right. And what dynamicists are interested in studying, well, it comes in basically 2 forms. One is what happens to points under repeated application of this function. Okay? So we say, for, say, some complex number, alpha, that the sequence of iterates that we get is the forward orbit of alpha. Okay? One thing that we might immediately be interested in is when this forward orbit is finite or not, right? So alpha is pre-periodic if this orbit is finite. And there's 2 ways that this can happen, right? If one way that this can happen is you're applying the function to alpha, and then eventually you come back to alpha where you started. That's a periodic point. The other is that you apply the function to alpha, and eventually you get back somewhere in the orbit, but not necessarily alpha. Okay? So the former I'll call periodic. Periodic points are one definition of special, yes, and I will talk about that a little bit. I see a couple more hands. Let me finish writing, otherwise my brain will forget it. Yes, somebody? Yeah. Yes, so that could definitely happen. Like, for example, well, I'm going to work through an example by hand, and I will mention which points do that. Yeah? Other questions? OK. So of course, this context, by the way, these definitions are totally general. Anytime you have a map on a set, you can ask this question, right? But I'm going to restrain myself and just look at polynomial dynamics for the moment. OK? So before I work through an example and hopefully answer some of those questions, let me give you a couple of more definitions. So this is one thing we're interested in dynamically, is looking at what happens to points. But we're also interested in understanding what happens everywhere at once, right? And let me move to a new board here. Wait, maybe I'll stick dynamics over here, and but then you can't see that. Nope, sorry. OK, so what do I mean by that? Well, let me first give you the definitions, and then we'll discuss them a little bit. So I'll define the Fa2 set of F is the collection of points where the iterates form a normal family. This means, by the way, that they're a precompact sequence, okay? But forget like the technical definition. What it means is that long-term behavior is stable on neighborhoods of points in this set, okay? If you know what happens at a point in the Fa2 set, then you know what happens to points nearby under long-term iteration, okay? So the way to really think about this is that it's the stable locus, meaning that a small perturbation doesn't change the dynamical behavior. Yeah? Yes, thank you. Yeah, in fact, I should sort of, that's a little bit nicer, thank you. OK. But really, OK, I mean, yes, this is useful because you're going to apply Montel's theorem all the time if you're in complex analysis. This is a useful criterion. But really, I want you to think in terms of perturbation stability, OK? And its complement is the Julia set. And we'll denote by that J of F, which, OK, sorry. And in fact, this is not quite right. Form a normal family on a neighborhood of the point C. I should also add that to be actually rigorous. And of course, you can write down a corresponding definition for the Julia set. But what you should think of it as is the chaotic locus. OK. And there's a lot of entertaining mathematical history, by the way. Fa2 and Julia were working at basically the same time, but one of them was a war hero and got all the credit, basically. So it's pretty interesting to read about if you are interested in these kinds of things, but I like that the sets are complements, that's all. All right. So, OK. So these are the basic objects that I study in complex dynamics, that we study in complex dynamics. We want to understand orbits of points, and we want to understand globally in the entire complex plane, where do we have stable dynamics and where do we have chaotic dynamics? OK, and speaking of aging myself, is Jurassic Park like too old of a movie for you all to have seen it? OK, so you know this scene? OK, so first of all, I realized that like I have Jeff Goldblum's job, basically. But so there's this scene where like he's sort of hitting on Laura Dern, and she's like, what's a chaos theorist? And he's like, OK, I'm going to tell you what a chaos theorist is. Like you hold your hand like this, and you drop a drop of water, and like sometimes it rolls this way, and sometimes it rolls that way, and it's chaos. That's what chaos is. And it's actually pretty solid. So what is chaos? It's a small perturbation changes the long-term behavior, right? And so in this dynamical system of dropping water onto my hand, right, this is the stable locus, this is a stable locus, and this is the chaotic locus, OK? So in fact, completely intuitive. I was trying to talk about my work to a group of 16-year-olds not too long ago, but I couldn't use that metaphor. I had to use like dropping a ball in a mountain or something. But OK. All right. They didn't think it was good. Anyways. OK. So these are the basic objects of study for complex dynamics. And as I was very intelligently asked, you've given me a definition of points which appear to be dynamically special, right? So can we use this interpretation? And the answer is yes, but I don't want to get to it yet. Let's work through an example so we can really get our hands on these objects first. OK, so here's the example I want to work through. Oh, let me use my crazy thing here. Put that back up so you can see it. OK, good. at least everyone can see that now. And okay, so here's the example we're going to work through. It's about the only one you can work through by hand, which is the squaring map. Okay. So let's let f of z, yeah, sorry, it's been a long process. Let's let f of z be z squared, okay? And I want to compute all of these dynamical definitions for this example. Okay, so first of all, we can write down explicitly what the iterates of this function are. That's why this is about the only one you can work out by hand. That's not generally the case, okay? So what is the nth iterate of this function? Well, we're just squaring, so squaring 4th power, 8th power, and so on. The nth iterate is just z to the 2 to the n. So knowing this, we can see right away what the pre-periodic points are. Well, they come in two different styles. They all satisfy some equation of the form z to the 2n is equal to z to the 2m. This can happen in two ways. Either z is equal to 0, or z is a root of unity. Right. And I'm actually going to put in a third possibility. Even though I'm talking about the complex plane, I can think of infinity as a fixed point for this dynamical system. Right? Okay. All right, so these are what the pre-periodic points are. Some of the roots of unity will be strictly periodic, and some of them will be strictly pre-periodic. This depends on which root of unity you take, right? And what then are the Fatu and Julia sets? Well, let's figure out where long-term behavior is stable.
If I take a 17th root of unity, why is that periodic or pre-periodic?
So this is the same thing as saying this, right? And so we know that every number divides one of these, right? For example, every number will divide 2 to the n minus 1 eventually, right? So, but for strictly periodic, really what you're asking for is that it's 1 less than a power of 2 for its root of unity, right? So in fact, yeah, you can really read it off of like which root of 1 it is. Okay. All right. So the Fatu and Julia sets. So what is the long-term behavior? Well, it depends on the complex modulus, right? So if I start with something with modulus greater than 1, right, then when I square this thing, the modulus increases. And then when I square it again, the modulus increases, and so on, exponentially. And so no matter what I start with, the long-term behavior of this thing is that it goes to infinity, right? So because we know that this goes to infinity, as n goes to infinity, the long-term behavior of any point with modulus greater than 1 is the same as any other point with modulus greater than 1. And so what that means is that the set of points with modulus greater than 1 is contained inside the Fatu set for this function. Okay, because they all do the same thing on an open neighborhood of themselves. Right? And similarly, if we take something with complex modulus less than 1, and we apply the squaring function repeatedly to it, the modulus gets smaller and smaller, and we're sucked into 0. Right? And so the open unit disk itself is also contained in the Fatu set. Right? So first of all, this is an answer to whoever asked about, can you have a point which sort of accumulates but is not pre-periodic? The answer is yes, right? Any of these points, for example, will get arbitrarily close to each other because they're getting arbitrarily close to 0, but they're not pre-periodic because they're not roots of unity. Okay. All right, so these two open sets are inside the Fatu set. But what about what's left? Well, we have the unit circle left, right? And points outside the unit circle go to infinity, and points inside the unit circle go to 0. And so the unit circle must be in the Julia set, right? Because if I take a point inside the unit circle and I wiggle it around a little bit, I can't tell what happens. Yeah? So it's exactly, this is my unit circle. It's exactly the definition of a chaotic point. And so the unit circle is inside the Julia set. And is, in fact, equal to the Julia set, since we know that everything else is in the Fatu set. OK. So that's about the only example you can work out by hand. Let me show you a couple of other examples that you can estimate with a computer. Stop. Ah. OK. Hey, OK. Ignore the object on the left, please. So, OK, let me tell you what this picture is doing. Let me first tell you what this is a picture of. So only look at the right half for now. OK, this is a picture of the complex plane. The yellow crosses at the origin. And the black circle, the scale is such that the black circle is the unit disk. OK? So what this algorithm is doing is it's taking this map, z goes to z squared, and it's iterating a point for a long time. And if that point eventually goes to infinity, it gets colored green. And if it doesn't, it gets colored black. OK? So what we're seeing here is the Fatu and Julia sets, but you need to be careful. The Julia set is the boundary between the green and the black. OK? So part of the black set is Fatu because we just showed that the open unit disk is in the Fatu set. OK? So the boundary of that black area is the Julia set for this function. But they don't normally look like this. So here's the Julia set for z squared plus I. Okay? The scale is the same. The yellow cross is still the center. This is still a picture of the complex plane. The Julia set is still the boundary between the black and the green, but actually now it's the entire black area because there's no interior for the black. Yeah?
So can you say a little bit more about your algorithm? Because this seems to be like a curve, like some kind of a one-dimensional Julia set. So how would you search for that?
So it's really doing literally what I said. So there's a theorem at work here that I haven't stated, which is that the Julia set is the boundary of the collection of points which go to infinity. Okay, this is a statement about all polynomials. It's not that hard to prove, actually. But so what this algorithm is doing is it's only testing whether or not something goes to infinity. Okay? And of course, it's just an approximation, though this is a connected Julia set. We'll see some disconnected ones in a second. It's just an approximation. The black points are the set of points which, after 1,000 iterates, have not gotten large. Does that clear up? Yeah? Other questions? OK. But there are still other possibilities. So here is z squared minus 1. Okay? Again, the Julia set is the boundary here. It still is sort of a fractal-looking thing, but it's not the spindly type like before, right? This is more similar to the unit circle case. And then just for contrast, here is the Julia set for z squared plus 1/2. Okay? So this is not a computer error. This is really a totally disconnected collection of dust. Okay? That's what the Julia set looks like in this case. All right? So you can estimate what these Julia sets look like, and of course you can prove things about them, but the point I want to make is that there's a lot of different types of behavior in terms of this dynamical characterization of what is the Julia set, what is the Fatu set. Okay? All right. So let me go back then to our z squared example, because I want to point out a couple of things about it that will be relevant. OK, so here it is. Good. So let me point out a couple of very important phenomena that are essentially at the heart of how we study these things and are true for polynomial dynamics in general, not just this z squared example. OK, so phenomena illustrated. OK, So the first is look at the pre-periodic points and the Julia set, right? Other than these two exceptional points of 0 and infinity, all of the pre-periodic points are contained in the Julia set, right? In fact, they form a dense, topologically dense subset, right? So this is, in fact, a general statement, which is that pre-periodic points are topologically dense. Man, you should not have invited me to a topology. Topologically dense subset of the Julia set. Like in the Euclidean topology on the complex plane, right? Not in Zariski or anything like that. Okay. In fact, it's not just topological density, right? These things are equidistributed with respect to a natural measure on the Julia set, which is the Lebesgue measure on the unit circle. Okay? So, in fact, you can replace this with measure theoretically. Equidistributed. And if you haven't seen this before, let me tell you what it means. So what does it mean to equidistribute in the measure theoretic sense? So it means that, so i.e., if I define, say, delta, bad notation. If I define, say, mu sub n to be a weighted probability measure, which is just given mass at the points of period n, okay, for example, say, so this is 1 over the number of points of period n times the sum over all period n points of the delta mass at that point, okay? Then this thing actually converges in the weak star topology to the Lebesgue measure on the unit circle. Okay, that is what I mean by equidistributed. And you don't have to just take period n. You could say, like, OK, I want pre-periodic with this length tail and then this period n, or whatever arrangement you like. As long as the period or the pre-period is growing, you will get this kind of equidistribution. Oh, I'm sorry. Did you have a question?
Well, it's about this. Is this special to this case, or is there a way of defining a natural measure on an arbitrary Julia set?
That's exactly right. There's a way of defining a natural measure on an arbitrary Julia set. I can tell you what it is, in one sense, which is that it's the equilibrium measure you get from Brownian motion at infinity. Okay, so if you drop a particle at infinity and you let it take a random walk, there's a measure supported on the Julia set which tells you the probability that that particle hits that part of the Julia set. Okay, that's what it is for a generic polynomial. Okay, but don't worry about it if you don't like potential theory and measure theory and all these things. You can just think about the topological density. Right? Okay. The other thing is that the same thing is true, actually, for preimages of a fixed point. Okay, so all of the above things, although it's not quite a dense subset of the Julia set, but the closure of the collection of preimages is actually the Julia set. So what am I talking about? If I take a point outside of the unit disk and I take its square roots, I get 2 square roots, which are negatives of each other. Then I take square roots again, and I get 4 fourth roots, which are related by rotation by I. And I take square root again, and it happens again. And each time the modulus is getting closer and closer to 1, right? What that's eventually going to give me, if I take that to infinity and take the closure, is all those points plus the Julia set. Yeah? So that's what I mean by this. And again, there's also a measure theoretic interpretation of this. And yes, this is also generally true for polynomials. But notice, it's not true if I started at 0, right? Because 0 only has one preimage. All right. And then the last but sort of most important thing I want to point out is that the critical point behavior are, well, critical. So first of all, by critical points here, I mean topologically ramified points, points that map with degree more than 1 to their image, right? So 0 and infinity in this case. What I mean by critical here is that they determine a lot of the dynamics, right? All of the points here that are not in the Julia set go to one of the critical points under iteration, right? And in fact, this is sort of the entirety of the interest of the study of complex dynamics, which is, think about it this way, right? A degree D map on the Riemann sphere, sending the Riemann sphere to itself. You've got one sphere, and then you cover it with degree D under the map, right? So it's generally an expanding map, okay? Now at critical points, the derivative is 0, and so it's locally contracting, right? And the tension between those two ideas is what creates the interesting dynamics. It's also why linear maps are not very interesting dynamically, okay? All right. Okay, so these three principles are generally true for polynomials and very important. Okay. All right, so that's my dynamical digression. I have one more definition I want to make before I sort of change gears again. Okay, so as was pointed out, one could certainly take a fixed dynamical system and ask about its pre-periodic points, right? Thinking of those as special points. And ask, okay, so when do I have infinitely many of those, and when do I not? The problem is that I'm talking about dynamics of the plane. And pre-periodic points and periodic points, just like up here, are cut out by polynomial relations. And in C, those always have roots. You'll always have infinitely many pre-periodic points. Okay, so let me write that down. Okay, so in polynomial dynamics, we always have infinitely many pre-periodic points. Because saying, for example, that the 100th iterate of a polynomial is equal to, I don't know, the 93rd iterate of a polynomial, right? The pre-periodic points which hit after 93 iterates, a cycle of length 7, right, satisfy this equation, right? And the roots of this thing will always be in the complex numbers, right? And we get different polynomials if we change these two numbers. So we get an infinite collection of polynomials, so we get infinitely many roots, so we get infinitely many pre-periodic points. And so the special points question is not such a good one in this context. Now that said, it's a great question overall, right? Because there's no reason to restrain yourself to doing dynamics of the Riemann sphere. You could take higher dimensional manifolds and do dynamics there. But I can't do that, so other people do that. So I'm going to rephrase this question in a different way, which is to look at families of dynamical systems and talk about special points there. Okay? So definition. And hopefully this definition seems reasonable to you given this third bullet point here, which is that we say F is post-critically finite. If all critical points are pre-periodic. Okay, and I'll denote this by PCF. Okay. So my claim is that these maps are dynamically special, the PCF maps. If you think back to what I said about the tension between the critical points and the global expansion, right? Forcing all of the critical points to have finite forward orbit is a very strong restriction on the dynamics that you can possibly obtain. Okay? Yeah, no problem. So here, critical for me. In the polynomial setting, you can really think of like polynomial critical points, and also maybe I want to think about infinity. Okay? So points where the derivative is 0 and infinity. But topologically, what I want to be thinking of is that locally my mapping degree is higher than 1, right? Okay, so we know that under polynomials, everything has a preimage, right? Again, by the fundamental theorem of algebra, everything has a preimage. Okay, but if it doesn't have the right number of preimages, then one of its preimages is critical. Yeah? Okay. All right. As you can imagine, generalizing this bit to higher dimensional dynamics is a little trickier. Yeah? All right. So, right, so these maps come with a bunch of additional structure. There's a ton of interesting work on these maps, a lot of which falls under the realm of Teichmuller theory. So if you're interested in that, then I'd be happy to tell you about it. Maybe not on everyone else's time. Yeah?
I apologize if you just said this, but does this mean infinity is always a critical?
For a polynomial, yes. But if I just take a general map of the Riemann sphere to itself, it doesn't have to be. Yeah, but I'm going to restrict myself to polynomials. One of the reasons why they're easier to study is exactly that, which is that infinity is critical, right? And in fact, it's better than that, right? You know what happens when things are really large under application of this polynomial. They always have to go to infinity. So that's the utility of making that assumption. Yeah. OK, good. All right, other questions before I continue? How is my time, Thomas? Sorry. Great, OK. So where was I? OK, so my claim is that these PCF maps are special. They're also, it turns out, special inside of families of dynamical systems. So I want to focus on a particular family. This will allow me to ask questions like the unlikely intersection question. All right, so in general, let me just define for you. So what do I mean by a family of dynamical systems? So if I fix a degree, then an algebraic family of dynamical systems is, well, I'm going to have to use algebraic geometry terminology here for a moment, so I apologize. I claimed that I would not need it, but I will be working only with one example, so I will not need it after this. But it's a morphism. In fact, let's just do with polynomials here. From some variety cross the complex numbers into the complex numbers, which sends a point on the variety to a polynomial of degree d. Okay, so this is the proper definition. Let me tell you what you should actually think about. So in some sense, the example that's most straightforward to study, but in a much deeper sense captures almost all polynomial dynamics, which is the family of quadratic polynomials, okay, where I've normalized here by making some conjugation so that I don't have a middle term. Okay? So this is a side comment, by the way. Conjugating your polynomial doesn't do anything other than move the dynamics around. Yeah? That's certainly an example. I mean, when I say variety, I'm really just thinking of like zero locus of polynomial equations in some large ambient Cn. Yeah? It doesn't have to be something that comes with additional structure or data or something like that. Yeah? And so just think of a curve, think of P1, think of the complex numbers like in the quadratic polynomial case. But I just wanted to put this definition here because of course you can ask the Zilber Pink question and you might want higher dimensions to do it. Sorry, yeah. Yeah, so I don't want to tell you. Sorry. No, it's really a very good question and totally legitimate, and I was hoping that nobody would ask it. So, yeah. But you should all take algebraic geometry if you haven't before. It's awesome. Okay. Wow, there was like disbelieving laughter at that one. Okay. Locally polynomial is the answer to your question. Okay. Like if you think about this case, right? What is this map then? It's the map that sends t and z to z squared plus t. That is definitely polynomial in t. Okay? So locally polynomial is what you should think of for morphisms, but I don't really want to be rigorous with it. Yeah. Okay. Other questions that I will dodge? Okay. All right. So I know it's irritating. I don't like doing it either, but sometimes it's just got to be done. Okay. So, but let's pay attention to this example. Z squared plus t, where t is a complex number. Okay? So just to finish up my comment from before, dynamicists generally don't care about what you do when you conjugate by something that has an inverse. So remark, if I took a quadratic polynomial that looked like, say, az squared plus zz plus c, then there's, so if f was this, then there exists some map, say, phi, which is az plus b, so that when I conjugate by composing f with phi and its inverse on either side, I get something of the form z squared plus t for some t. Okay? And so to a dynamicist, these are all the quadratic polynomials. Yeah? Okay. All right, so here's the family I'm interested in. I want to tell you where the PCF maps lie in this family, because I want to convince you that they're dynamically special. That's why. I want to apply the Zilber Pink theory to this setting, but that doesn't make any sense unless I can justify to you that this is actually a good notion of special. Okay? All right, so where are they? Let me show you. I don't want to bring this all the way down. Okay. So you may now look at the left-hand side of the board. Okay. So there's an object in black here, which I need to define for you. So again, going with my notion here, that critical points are important, right? And infinity is important for polynomials, right? Notice that a polynomial of this form has only one finite critical point, namely 0, right? Okay, maybe we think of infinity as 1 also, but as far as the complex plane is concerned, there's only one critical point, and it's at 0. And so we're going to distinguish between when that point 0 goes to infinity and when it doesn't. And the Mandelbrot set is the collection of complex parameters t such that the iterative 0 under the map, so this is defined to be z squared plus t, where the iterative 0 under this quadratic polynomial does not go to infinity. Does not go to infinity, meaning that its modulus doesn't go to infinity. Okay, it remains bounded in the complex plane. In fact, it remains bounded by 2 in the complex plane, which if you start writing down the polynomials, you can prove by induction. Okay? All right. So there's a picture on the left. Again, let me orient you. This is a picture of the complex plane, and it's to basically the exact same scale, which let me put back up. It's to basically the same scale as the right-hand side, okay? But it's a little bit broader view. So like I said, this whole thing is contained in the disk of radius 2 about the origin. The yellow cross is now at the origin in the complex plane. And the leftmost bit there is really -2 on the nose. Okay, so that's the real axis that we have a symmetry about. Okay, which shouldn't be surprising because the orbit of 0 will behave pretty well with respect to complex conjugation of the parameter, right? You'll get the same behavior either way. Okay, so the way this picture is drawn is exactly the same way that the individual Julia sets were drawn, which is that we take 0 now, not just any point in the complex plane, but 0, and we iterate it like 10,000 times. And if eventually it's bigger than 2, then we color it green, and if not, then we color it black. Okay, and that's how pictures of the Mandelbrot set are drawn. Counting how many iterates it takes you to get large, by the way, if you're not in the Mandelbrot set, is how the fancy colored pictures are drawn. Okay? But I just wanted to show the two cases here. All right? There's another characterization here in terms of connectedness of the Julia sets that's super fun, but not relevant at the moment. Okay. All right, so where are the PCF maps? Okay, well, let's find some first. Okay, so what are the PCF maps in this family? When we think of the complex numbers as parametrizing quadratic polynomials, right? Well, we could certainly ask, okay, first of all, to figure out if something is PCF, we just look at 0, right? Since it's the only critical point. So we look at the types of dynamics that 0 could have. So here's one possibility, right? If 0 has finite forward orbit, maybe it's because 0 is fixed. That's the parameter t equals 0, right? That's where the yellow cross is. That is certainly in the Mandelbrot set, right? Or maybe we could ask that 0 maps to something else and then comes back to itself. If you write out the polynomial equation, 0 squared plus t squared plus t equals 0, you get 2 roots here to t squared plus t. One of them is 0, which, oops, is the degenerate situation of this picture. And one of them is minus 1, which is the center of that little disk. Let's see if I can pick it out here. Which is the center of that little disk on the left-hand side of the main cardioid. Okay? And here's another PCF map. And here's another PCF map. And here's another PCF map. And generally speaking, inside each component that you can see is exactly one PCF map, right in the center. Okay? So these kinds of PCF maps inside the Mandelbrot set, where 0 is strictly periodic, okay, are known as hyperbolic centers. But there's another kind, right? We could also have asked for 0 to map to something which maps to something else, which is then fixed, for example. By the way, we could not ask for this, right? Because 0 maps with degree 2, and so it's a unique preimage of whatever it maps to. Yeah? Okay, but we could ask for this. This certainly happens. And did I pick the right one? Do I want that one? 0. Yeah, and that happens at minus 2 here, I think. I might be forgetting. Minus 2, 2, 2. Yeah, that happens at minus 2. Okay? Similarly, the one Julia said I showed you earlier with the parameter I, that also happens to be a PCF map with a slightly more complicated portrait that I don't remember off the top of my head. Okay? So minus 2 is the left-hand side of this picture, whereas I, oops, there it is. Can you see the yellow cross up on the upper right-hand side of this picture? That's where I is, okay? And we can do a few more, but the point is that this other kind of PCF map, this other kind will always lie on the boundary. But in fact, it's better. So these pre-periodic types are on the boundary of the Mandelbrot set. But in fact, it gets better. They're topologically dense in the boundary of the Mandelbrot set. Okay? So this is one reason why they're dynamically special, is that they pick out for you the boundary of the Mandelbrot set. Yeah? Oh, 5 minutes. Thank you. So yes, so that is where I am headed, except I can't get my chalkboard down. Hold on. So then you can say, well, I've seen topologically dense things pick out these sort of fractally looking objects before in complex dynamics. Does it hold in the parameter space, right? And the answer is yes. Okay? So okay, so some facts is, as was guessed here, PCF maps are not only topologically dense, but equidistributed with respect to a natural measure. But let's just stick with topologically dense if you don't like that. And the natural measure is the same one as the polynomial Julia sets, which is I let a particle free at infinity to take a random walk, and the measure, which is supported on the boundary of the Mandelbrot set, tells me how likely it is to hit that portion of the boundary of the Mandelbrot set. Okay? But topological density is enough for my purposes. Okay? So these maps are really dynamically special. And so we can ask, okay, great. I have this parameter space, C. It's a curve. I have PCF maps, which are dynamically special. How many does it have? Right? Okay, but again, requiring these kinds of orbits is a polynomial restriction. And there's infinitely many of them. And so the fundamental theorem of algebra tells you easily that you've got infinitely many, almost, once you know that they're all different polynomials. Okay? So in fact, there are infinitely many. This is a little bit implied by what I just said above, of course, in the family of quadratic polynomials. Okay, but nonetheless, we can ask a Zilber Pink question. And the way we can do it is by thinking back to faultings, right? What did rational point mean in faultings? It meant that both coordinates were rational. So instead of thinking of a single dynamical system, why don't I take two and require that both of them be PCF for my meaning of special points? Okay? So with, 2 minutes to spare, there will be a theorem on this board. So this is due to myself and my co-authors, Ghioca and Nguyen, and then another piece of it to finish the argument with Heshi Yi, which is that if you let C be an irreducible algebraic curve in C2. So again, this is just the collection of zeros of some, I won't call it F, there's too many of those around. The collection of zeros which satisfy some polynomial equation, okay? Then C has infinitely many points, x, y, such that both z squared plus x and z squared plus y are PCF only if C is a line. Okay. So let me say a couple of remarks. Okay, so this is an unlikely intersections statement in complex dynamics, right? And the way to interpret it in this context is that for these pairs of dynamical systems, there are no special curves, right? Except for the sort of silly ones like vertical and horizontal lines and the diagonal. Okay? All right. So let me finish with just a couple of remarks. So one is that even though everything I've said has been a sort of like by analogy, or let's apply the principle to the dynamical setting, blah, 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 you should be advised that there is a real connection between arithmetic geometry and complex dynamical systems. remark, there is a deeper connection than I have sort of implied to arithmetic geometry via the theory of height functions. So I saw a couple of titles on elliptic curves in the talks that are to come today and tomorrow. So if you've worked with elliptic curves, you know that they come equipped with height functions. There's an analog of this in the complex dynamical setting, which provides the basis for how to prove these things. Okay? So this is remark 1. Remark 2 is that the other heart of this kind of proof, really every proof of statements like this about unlikely intersections in complex dynamics, and there are sort of a constellation of statements like this which have been produced in the last 5 years using sort of the same program of proof, which is that complex dynamics, or the Mandelbrot set, and algebra don't mix. So what do I mean by that? I mean that the curve I took up here was an algebraic curve. It's cut out by polynomials. Okay? And one of the key ingredients in the proof here, and a similar strategy is needed in any analogous proof, is that there is no algebraic correspondence which fixes the Mandelbrot set. Okay? Or more simply stated, don't worry about correspondences, there's no function, which is a polynomial function, which fixes the Mandelbrot set. Okay? And the reason why, in my last minute, is because the Mandelbrot set sees the dynamics of all of its PCF parameters. Okay? Let me demonstrate for you what I mean. Let's go back to I. Okay? So what is happening? So the yellow cross on the left-hand side is at the parameter I inside the Mandelbrot set, because I mentioned to you that it's actually a PCF map. On the right-hand side is the Julia set of z squared plus I. And now what I'm going to do is I'm going to zoom in on the left-hand side on the point I. Okay? And I'm zooming. Let me recalibrate a little. And I'm zooming, and I'm zooming. And the closer I get to z squared plus I, the more the boundary of the Mandelbrot set looks like the Julia set for z squared plus I. Okay? Which, just so you all know, I know there hasn't been that much coffee, is shocking information. Right? So this is true no matter where you go in the Mandelbrot set. So I said -2 was also 1. Right? So here's -2 on the left now, and here's its Julia set on the right. It's actually an interval, by the way. Okay? This is one of the only other ones you can work out by hand. And if you start zooming in to -2 in the Mandelbrot set, same thing. Okay? So the Mandelbrot set sees the complex dynamics of all of these PCF parameters, which means if I had a function which fixed it, which sent it to itself, somehow I would be sending the complex dynamics of one function to the complex dynamics of another function. And that just can't happen. Okay? And maybe I should stop there. Thank you.
On the right, are there computational artifacts showing up, or is it
yeah, looks like there's a little noise there. But for -2, it really is the interval. Yeah, it's an interval contained in the real line. There's none of this vertical mess.
Okay. And is the statement just about some small neighborhood of the Julia set?
So it's a little bit more careful than that. Okay, so if you have, so the notion is of asymptotic self-similarity, okay, which is that there's a topological model you can make of a Julia set, which is less complicated than the Julia set itself. So think about, like, let's go back. Let's use a less straightforward one than this one. So if we go back to I like I. Let's stick with that. Right, like this is a pretty complicated set, and it's hard to sort of describe. But as you can imagine, there's like a pretty straightforward topological model of this thing, where you take this skeleton and then you require that it look like that everywhere, basically, or on a dense set of points. Okay? And so what this actual statement is, this is a theorem due to Tanlei, who just passed away, actually, but last year, I think. But what she proved is that you have this asymptotic self-similarity, meaning that if you do exactly what the picture is doing, meaning you rescale and you zoom, but with the right level of zoom and rotation at each step, then what you get converges to this topological model, whether you're looking at the Julia set or at the boundary of the Mandelbrot set at the point. Okay, so it is a local statement in the sense that you're looking around the point a little bit, but it's requiring that you zoom in infinitely far. Yeah?
And is that a local model for the Julia set too, or does it describe the whole Julia set?
I'm sorry?
Is it a local model for the Julia set, or does it describe the whole Julia set?
Well, so that's another, that's another piece of the puzzle, or argument, or whatever, which is that actually the Julia set is itself self-similar, which means that it doesn't matter where you look. If you zoom in into the Julia set with the right lens, then it looks the same everywhere. Yeah. So local is global. Yeah. Any other questions? Yeah.
What's the practical dimension, Hausdorff dimension of this Mandelbrot set?
So it's 2. This is a result of Shishikura. In fact, he goes through this analogy, right, that a generic Julia set has Hausdorff dimension 2. Shishikura.
Oh, I'm sorry.
Yeah. No, it's fine. But for any particular Julia set, it's actually pretty hard to say what the Hausdorff dimension is. Yeah. There's a lot of stuff that I haven't talked about today about like local dynamics around periodic points, but those are the kind of techniques that you need to answer that kind of question and to show the self-similarity of the Julia set, actually. Yeah. Any others? Okay. Well, I'm around, so one-on-one questions are welcome for the rest of the weekend. Thank you.